Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your main topic, that is integration, we are going to take another new aspect under this main topic. And this aspect is now application of integration. And one of the area we consider first is area under the curve. So let's begin. After completing the very lesson today, my dear student will be able to find the area between the curve and the x-axis. This is what I hope you'll be able to find this very area between the curve and the x-axis. My dear student, in your favorite segment of the lesson, that is Mercy Fun, today I'll give you another interesting number, and this number is 9. I will explain what is interesting with this very number right after completing my lesson today, so don't go away. To begin the lesson, my dear student, you needed to know that the definite integral is what we used to find as a scale to find the area under the curve, and that area under the curve could be area between the curve and the x-axis, or it could be area between the curve and another straight line. These are the two concepts that we are going to take in this very lesson. But for the sake of this very lesson, we are going to take the very first one, that is learning how to find the area between the curve and the x-axis. In our next lesson, we are going to take the second part, that is finding area between the curve and another straight line. But what we now use, the skill that is needed here, that is required here, is your definite integral, which we learned in our previous lesson. So let me just move and take the very first case, that is area between the curve and the x-axis. So the area between the curve and the x-axis, so suppose you have the curve y equals to f of x. This is a curve, as you can see here displayed. This is your Cartesian plane, and this is the curve y equals to f of x. So the area A, that is this area of this shaded portion, between the curve and the x-axis. Look at your x-axis, that is the area enclosed by this, the x-axis and the curve. Look at it, this is the shaded portion denoted by capital letter A. So this area A between this curve y equals to f of x and the x-axis from the point x equals to A. Look at it in the drawing. This is at this very point, the value of x here is A, and at this very point, the value of x there is B. So from x equals to A to x equals to B, this is the points of intersection of the curve and the x-axis. So this area would now be given by this simple formula, area A equals to the definite integral from A to B of the function, that is of the curve f of x with respect to x. So what you simply do to find the area between the curve and the x-axis is to find this integral, that is the definite integral of the function between these limits, that is A as the lower limit and the B as your higher limit. If you now find the definite integral of that very function, what you have in the end is now the area between that very curve and the x-axis. We are going to make use of this very formula and solve two or more problems finding area between the curve and the x-axis. So let's just move and take examples. Example number 1, you asked to find the area between the curve y equals to x squared and the x-axis from this point x equals to 2 to the other point x equals to 5. Solution to this very problem. There, what we do first is to write down the formula or the rule of finding area between the curve and the x-axis, which says area A equals to the definite integral from the lower limit A to the higher limit B of the function O of the curve f of x with respect to x. So what I'm going to do now is to find the definite integral, but this is my function f, that is this f of x is now y equals to x squared. Let me get the limit first. The limit, that is the integral, but in this case is the definite integral. So A is my lower limit while B is my higher limit. From the question, if I go back to the question, it says from x equals to 2 to x equals to 5. So this 2 will now be your lower limit, while 5 will now be your higher limit. So let me write the definite integral from 2, that is the lower limit, to x equals to 5, that is my higher limit of the original function, that is the curve, and the curve is f of x, which in this case is now x squared. So the function x squared, and I'm going to find this integral with respect to x. So I continue. So I now find the definite integral of x squared, or the integral rather of this x squared before finding the definite integral. So the integral of x squared is now going to be x raised to 3 all over 3, then plus the constant of integration. Then I copied those limits, lower limit to higher limit 5. So I'm going to substitute, starting with the higher limit, replace the x by the higher limit, finding the result. Replace the x by the lower limit, finding the result. And those two results, you now subtract. That will give you the area, which is the definite integral. So I continue. So substituting the higher limit, that is, I'm replacing x by 5. So I'm going to have 5 raised to 3 all over 3. I have replaced this x by the higher limit 5, then minus, now replacing the lower limit instead x. So you now have 2 raised to the power of 3 all over 3. So I continue. So I'll now find these values. 5 raised to 3 and 2 raised to 3. 5 raised to 3 is now going to be 125 divided by 3 minus 2 raised to 3 is now going to be 8 over 3. So I'm now going to subtract these two fractions. They have same denominator 3. So after using LCM correctly, you now have 39 square units. This will now be the area between this very curve and the x-axis at this very point, x equals to 2 to x equals to 5. Let me take one more example. Example number 2, you asked to find the area between the curve. This is the curve y equals to 4 minus x squared and the x-axis. Solution to this very problem. So what we do first is to write down the formula or the rule, finding area between the curve and the x-axis. And this is the rule. It says A for the area equals to the definite integral from A to B of the curve f of x with respect to x. So in this case, I'm now going to write integral from A to B. Now let me just get my limits there. A is the lower limit, B is the higher limit. In the previous examples, we have those limits, but in this case, we don't have the limits. So what I'm going to do is to find those limits, and those limits will now be the value of x at the 2 points where this curve crosses the x-axis. So to do that, what I'm going to now do is to solve this very equation. 4 minus x squared equals to 0. So I'm now finding where this curve 4 minus x squared crosses the x-axis. That will give me the value of x. That is the solution of this very equation. So solving this 4 can be written 2 raised to the power of 2. So you have 2 raised to 2 minus x raised to 2. That will now make you to think of the difference of 2 squares, and the factorization of this would now be 2 minus x in one bracket, and the other bracket is 2 plus x. So we have these two brackets multiplied together to get 0. So one of this bracket definitely will be 0, or both of them are zeros. So if the first one is 0, x will now be 2. If it is the second bracket that is 0, then x will now be minus 2. So these are the 2 points where the curve crosses the x-axis, and that will give us our lower and the higher limits. So in this case, the smaller one, which is minus 2, will now be the lower limit, and the higher one will now be your higher limit, which is 2. So then now go back to this my rule. I'll now have the lower limit as minus 2 and the higher limit as the 2 of, that is the definite integral from minus 2 to 2 of this curve, which is 4 minus x squared, then with respect to x. So what remains is to find this integral. Finding the integral, you now use that integral function and substitute those limits and subtract the two results. Let me go on and do that. So integral of 4, that will be 4x. And integral of x squared, that will now be x raised to 3 all over 3. Then plus the constant of integration. Then I copied those limits. So I'm substituting the higher limit and the lower limit in this integral function. This is the integral of the curve 4 minus x squared. So starting with the higher limit, which is 2, replacing x by 2, I'm going to have 4 times 2. I have replaced this x by 2. Then minus x raised to 3. So I'll now have 2 raised to 3. I'm starting with the higher limit. Then minus. Then I'll now replace the lower limit in this integral function. That will give me 4 times minus 2. Then minus 2 raised to the power of 3 all over 3. So I'll continue. So I'm now going to find the result of each of this. So this is 4 times 2, which gives me 8. And 2 raised to 3 is 8 over 3. So using LCM to do this subtraction, if done correctly, you're now going to have 16 over 3. And this very one, if you did it correctly, you now have 16 over 3 as well. So adding 16 over 3 and 16 over 3, adding these two fractions and dividing by the denominator, which is 3, you're now going to have 10.6667 square unit as the area between this curve and the x-axis. My dear student, this is the end of this very lesson. I hope with the few examples given, you'll be able to find the area between the curve and the x-axis. And this is, let me just move to the last segment of the lesson, that is maths is fun, and give you something interesting about the number 9. Dividing any digit by, that is any digit between 1 to 8 by this number 9. That is dividing 1 by 9, 2 by 9, 3 by 9, up to this number 8 by 9. What we are going to have as a result, the result will always give the digit, that is that very number that you have divided, and that digit will now be repeated to infinity. That means it is now going to be an irrational number. So let me just start dividing the very first number. So I have 1. This is 1 divided by 9. This is now going to be, if you do it correctly with your calculator, you have 0.111111, and those one keep repeating without end. Let me take the next digit, which is 2. So dividing 2 by 9, that is 2 divided by 9. If you do it with your calculator correctly, you now have this very digit repeated to infinity. That is 0.22222. If you do it with the calculator, you see this is what you are going to have as your result. Let me take the next number, which is 3. 3 divided by 9. According to this very property, it says I'm going to have this very digit 3 and repeated it to infinity. So if you do it with your calculator, I'm sure you get this 0.3333 each, and it continues. Let me just take a last one, 4 divided by 9. So the result is now going to be 4 each, and it continues to infinity. So if you do it with the calculator, this is what I believe you get from your screen. And you can take other numbers 5, 6, 7, and 8 and keep dividing or divide them by 9. You get that very number that you have divided but repeated it to infinity. This is really interesting, which I believe also you never noticed. Thank you for your attention. We see more of this in math.